Okay, so welcome to the first in a set of videos that will be a guide or a walkthrough of the 2019 Regents Physics exam. This is about a month ago. What I've done is I've gone through the exam, I've marked it up as much as I can, and my goal for this is basically to give you an idea of what you should be thinking about as you look through these questions. As I'm making this, I'm not really sure how I'm going to utilize this video. I can do a number of different things with it, but it was something that I wanted to start doing. I've seen other people do Regents, kind of going over the Regents exams in video style, and I kind of wanted to try it. So that's what we're going to be doing today. So let's get started. The first part of the Regents, there are 35 questions in part A. They're all multiple choice questions. Usually these are the easier multiple choice questions. That's not to say that there aren't hard questions in there, but these are typically the easier ones, or maybe a better way of describing it, slightly less calculation than the last 15 multiple choice. Let's get started. The first question on every Regents I have seen for at least the past 10 years is some sort of scalar vector question. You need to know the difference between a scalar quantity and a vector quantity. And as you hopefully remember, scalar quantities, that means that there is no direction necessary in order to fully describe whatever measurement it is. Okay? Whereas a vector, you need to say not only the magnitude, the size of the measurement, you also need to talk about what direction that measurement is oriented in. Really, scalars and vectors just comes down to you having to memorize which measurement is which type. Okay? You need to memorize what are scalars and which ones are vectors. So let's go through the list. First question, displacement and velocity. These are both vectors, okay? Displacement is a vector, velocity is a vector. Displacement means how far, it means what is the length of a straight line path between your start point and end point. And the direction also matters. For displacement, it matters if you are displaced to the north or to the south. The analog to displacement, the scalar version, if you will, of displacement is distance. That is like a total path length. So that's a vector. Velocity is displacement divided by time. And since it's displacement divided by time and not distance divided by time, velocity must be a vector as well. You see V stands for velocity. Okay? Speed, on the other hand, is distance divided by time. And speed starts with an S, and speed is a scalar. So anytime we see either displacement or velocity, we know that that cannot be the answer. Which pair represents scalar quantities? So that means this is a vector, that's out, that's out. We have velocity, that's out, energy, and time. At no point in the year have we ever described energy as needing a direction. You don't have 100 joules of kinetic energy east. You just have 100 joules of kinetic energy. Time is similar. Okay? We don't say 5 seconds west. Now where that gets confusing is we do kind of talk about that when we are in casual conversation. Syracuse is an hour east of Utica, or hour west of Utica, excuse me. But that is not very good language, okay? Time is actually a scalar. Both these are scalars, therefore the answer is number 4. That was a lot of talking for question 1. Let's try and speed it up a little bit. Question number 2. Sailboat on a lake sails 40 meters north and then sails 40 meters due east. Compared to its starting position, the new position of the sailboat is. This is another vector question. They're getting at more of the mathematical treatment of vectors. Let's map out what this sailboat does. Sails 40 meters north, then sails 40 meters due east. We'll say that this is 40 meters north. Here's 40 meters east. Compared to its starting position right here, the new position out here is, well, let's see, look at these first two. 40 meters due east. No, it's definitely not just east. It's also up to the north. It's definitely not due north. Neither of these make any sense. You have 2 options left. 57 meters northeast, possibly. 80 meters northeast, possibly. If I were to measure this right here, okay, then I'm in exactly the same spot. If I were to measure this right here, okay, I need to know whether this vector, this length, is 57 meters or 80 meters. The only way that this would be 80 meters is if you had 2 vectors, 2 motions, that were in the exact same direction. For instance, maybe this and then this. If each of these are 40, you can very clearly tell that this is 80. But this second vector is not in the same direction as the first. It's off to the side. It's pointing to the east. So you can kind of probably guess that this distance is probably not 80 meters northeast. Without doing any math, you should be able at this point in the year to tell that the starting point is, or that the ending point is 57 meters northeast from the starting point. If you wanted to do math to prove that, look what sort of shape we have here. That's a right triangle. We're looking for this side. We have the two legs of the right triangle. We could use a squared plus b squared equals c squared. Plug in 40 squared here, 40 squared here, or 40 here, 40 here. Square both of them, add them together, take the square root. You will get 57. I'm not going to go over that right now. Okay, number 3, getting into a little bit more kinematics, a little more physics, as you guys would probably want. A ball is thrown straight upward from the surface of Earth. Which statement best describes the ball's velocity and acceleration at the top of its flight? This is another one that it's kind of halfway between a memorization question and it also just kind of, well, at this point in the year, it should just make sense. If I were to toss something, ball is thrown straight upward from the surface of Earth, okay, I throw the ball straight up and it comes back down, then you should be able to tell me something about the top. When it's at the peak of its motion, that means it's not going up any higher, right? But has it necessarily started to fall yet? No. So if it's not going up, and it's also not going down, and the ball was thrown straight upwards, it's not moving side to side, what does that mean about its velocity? The velocity must be 0 at that point. So anything that says the velocity is non-zero cannot be correct. Okay, so that would be 3 and 4. These are not correct, leaving us 1 and 2. Both velocity and acceleration are 0, or velocity is 0 and acceleration is non-zero. This is where you need to have a good idea and definition of what acceleration is. Velocity is essentially, well, let me back up. The scalar counterpart to velocity is speed, okay? How fast something is moving. Acceleration does not mean how fast something is moving. Acceleration means how much is the speed, or really how much is the velocity of that object changing per second. And you might be tempted to say, well, it's not moving, therefore the velocity is not changing, and therefore the acceleration is also 0. But if that were the case, if the velocity was 0 and the acceleration was 0, meaning the velocity is not changing and the velocity is 0, wouldn't that mean the velocity has to stay 0 the whole time? And if the velocity stays 0 forever, doesn't that mean the ball would just stay here? I don't know of any ball that I could toss up and just have it stay there permanently, forever, if this is in free fall, okay? We're just tossing it up, letting it come back down. It doesn't make any sense to say the acceleration is 0 because then the ball would get stuck up there and it wouldn't ever move again. It would never fall back down. The acceleration cannot be 0. And as many of you have probably noticed, this ball is in free fall. We know the acceleration of a ball in free fall. 9.81 meters per second squared towards the ground if we are throwing something on Earth. The only answer that makes sense is number 2. Okay? All right, moving on to number 4. As I erase, I'll read it. As a student runs a plastic comb through her hair, the comb acquires a negative electric charge. The charge results from the transfer of what? We're jumping all the way to electricity. Sometimes that happens. Usually it seems like they kind of go in the order that we cover stuff throughout the year. I guess they're not right now. We're jumping right to an electricity question. This question is getting at the heart of the question of what type of charge is allowed to move. So think back to chemistry. Think about the charged particles that you dealt with in chemistry. You had protons, you had electrons. Okay? The protons were locked in the nucleus, along with the neutrons. They didn't really ever leave the nucleus. They stayed in there. Chemistry was all about what happens with those electrons on the outside in the outer orbits. Because when you bond things together, sometimes those electrons get shared, sometimes they get ripped off of one atom and put onto another, creating an ion. The electrons could move around, and that dictated how chemical reactions worked. And it also is just a general rule that typically protons are going to stay in their nuclei. They can't move. The electrons are the only particles that can move, and that's the rule that we've been using all year. Only electrons can move. protons stay in the nucleus. Okay. Now, that means that any of the answers that talk about the transfer of protons, that's not going to cut it, okay? There's no nuclear reactions going on here. There are electrons being moved from one object to the next. The question says the comb acquires a negative electric charge. That means the comb must be gaining electrons. Remember, electrons are negative. If the comb is gaining electrons, that means the electrons must be going to the comb. Electrons moving from her hair to the comb, meaning her hair now has a positive charge, just lost a whole bunch of electrons. Electrons transferring from the comb to her hair might sound right because the charge is negative, but you have to remember electrons are negative themselves. Okay? Whatever object gains electrons must be negative, or is becoming more negative, I should say. So that's answer number 4. 5. How would the mass and weight of an object on the moon compare to the mass and weight of the same object on Earth? The key here is we have two different words that you might think means the same thing. They do not. Okay? Mass. Mass is the amount of matter in an object. Okay? The amount of stuff, the amount of protons, neutrons, and electrons. If you take an object and bring it to the moon, it's going to have the same amount of stuff in it. It's going to have the same amount of protons, same amount of neutrons, same amount of electrons. You didn't change how much matter there is. The mass will stay the same, no matter where you take it. The only way to change the mass of something is to physically remove or add on some matter. If you were to take this ball, for instance, and bring it to the moon, it would have the same mass, unless I chopped the ball in half, or unless I took some clay or some moon dust and I threw it on the ball, and now the ball has more matter attached to it. That's the only way the mass can change, if you add or subtract matter. Weight, on the other hand, is not simply the amount of matter. Okay? Weight is just another word for the force of gravity. Okay? And the force of gravity changes based on location. It will change based on where you are. So the answer to this one, you need to know the definitions of mass and weight. Let's see, the mass would be the same, but weight would be less on the moon. Mass would be... Okay, that's the only one that makes sense. All right, mass would be the same, but the weight will change. The reason the weight changes is because the moon has a good amount less mass than the Earth. And when we get into, well, we did this year talk about gravitation. The gravitation equation depends on the mass of not only the object that's on the moon, but also the mass of the moon itself, or the mass of whatever body it happens to be sitting on. So mass would be the same, the weight would be less on the moon because the moon is generally smaller in terms of its mass. So, that answers number 2. Let's slide over to the right-hand column. Look at those questions. Okay, 6. Going to circular motion. We're really hitting a lot of stuff right now in this beginning. An object is moving with constant speed in a circular path. Okay, constant speed. Notice that word speed, it says is constant. Circular path. The object's centripetal acceleration, remember the symbol for this is AC, A sub C, remains constant in magnitude only, direction only, both magnitude and direction, or neither magnitude nor direction. Here's the orbit of an object. Okay, let's say the object is right here right now, moving around some central point. Let's say it's moving counterclockwise. That means that the object at this point, when it's at the top of the circle, is moving this way. There's the speed, there's the velocity of that object at this one point. Okay? Now, the other vectors that we learned how to draw, the centripetal force and the centripetal acceleration points directly in. This is how the picture has to be drawn. If something is moving, I guess in this case to the left, but the acceleration is down, that will cause the object to move in a curved path, to not move directly in either of these directions, but to kind of take an intermediate direction. And as the object moves around its, it's changing direction, so that down right here, now the velocity looks a little bit more like this. the centripetal force and acceleration are still in towards the center, that will change the direction of its motion even more. So as it goes, the direction of all these vectors changes the entire time. Okay? That is why we have objects that can move in circles. The direction of all of these vectors will change over time as it makes different orbits or as it completes revolutions. So, how does the centripetal acceleration remain constant? We know the direction doesn't remain constant because we just got done saying that these vectors change as the object moves around. So direction only, it does not remain, so those two can't work. Now we just need to know if the magnitude stays the same. And if we're talking about magnitude, that kind of hints that we need the equation from our reference tables, AC equals V squared over R. V in this case, and this is something you have to remember, stands for the speed. We are told that it's a constant speed. R is the radius of the circle, the orbit, the revolution that the object is moving around. If it's a circle, that means the radius is constant. V is constant, R is constant, that means AC is constant, the magnitude is constant. We know the direction isn't constant, but the magnitude is constant. The centripetal acceleration is the same at all points in that object's motion at that particular speed. So that is choice 1. Number 7, as shown in the diagram below, rope attached to a 500 kilogram crate is used to exert a force of 45 newtons at an angle of 65 degrees above the horizontal. The horizontal component of the crate, of the force acting on the crate, is what? There are equations for this in the reference tables. I do not spend a lot of time going over them because most of the time it seems pretty innate by this point. I know some of you do still struggle with vectors and splitting them into components. Think of it like a trig problem, okay? You have this. You are asked for a horizontal component. That means the extent of this vector in the horizontal direction. That's what we're looking for. How big is this? If this is 45 newtons, how big is this? And you've got to visualize this for a second. What would a vertical component look like? Well, it would look like this. And I'm going to take that vertical component and I'm going to move it to make this problem look a little bit easier. The reason this makes it look easier is what shape did I just create? I just created a right triangle. And you now have a right triangle where, and I drew over the degree sign obviously, you know this angle and you know the size of this right here. You should be able to use trig. You've been using this trig since you were in either 8th or 9th grade. You should be able to use this trig to figure out how big the horizontal component is. We have a hypotenuse. That's this side right here. We're looking for the x component, the horizontal component. We have the angle. We would refer to this component, if the angle is right here, we refer to this as the adjacent side. So we know adjacent, or we're looking for adjacent. We know the hypotenuse. Which trig function is that? That would be cosine. Cosine 65 degrees equals x over 45 newtons. I rearrange this. I get x by itself, meaning I multiply both sides by 45 newtons. I come out with this. 45 newtons times the cosine of 65 degrees equals x. Therefore, x equals, let's see here, about 19 newtons. That would be choice number 1. And this relates to our equation that is in our reference tables. If you look on the back, there is an equation that says ax equals a cosine theta. Meaning, any x component, typically, for any sort of vector, is equal to the size of the big vector, the vector you're given, multiplied by cosine of whatever the angle is. That is, in fact, on the reference tables. Last one on the front page. A spring with spring constant of 68 newtons per meter hangs from a ceiling. When a 12 Newton downward force is applied to the free end of the spring stretches a total distance of what? So we have a spring hanging from the ceiling. We are simply putting a 12 Newton downward force on this. We want to know how far it stretches. This is a forces question. The equation is on the reference tables. The equation that you need to use, well actually first let's go through what we know. Spring constant of 68 newtons per meter. This is something I really like to do. Let's label everything right now. We know that that's K. Okay, lowercase k, spring constant. Don't get that confused with electrostatic constant. A 12 Newton force is applied to the spring. They force on a spring. We call that Fs. The spring stretches a total distance of what? Stretches a total distance, that is x, okay? Distance stretched or compressed from equilibrium. We put all those together. The equation that we use, that is on the reference tables, which you learned, is the spring force is equal to the spring constant multiplied by the total distance it stretches from equilibrium. It's a 12 Newton force. It's a 68 Newton per meter spring constant. We solve for x by dividing a 68 over. We end up with about 0.18 meters. That again is answer number 1. There's the first page. I'll be back for the second.